Yo. So I found out, looked at my email a little bit more closely, that the meeting that I have tomorrow is not just with somebody who's like, doing similar research and, of the interest area, but he is, one of the chief AI scientists for the entire lab. So I need to be more prepared. Just to like sanity check, I'm gonna walk through the slides that I prepared based on like the informal discussion that we had yesterday, just to get my brain cooking a little bit. We spent this morning kind of dealing with some OBS things. We're testing at 2K resolution now. I want to use one resolution because we're on a Mac computer for the second machine. So to kind of balance between YouTube and Twitch, live and non-live, I have Matt 2K instead of 4K or 1920. We'll see how it goes. Yeah, I don't think YouTube needs to be that high res. Anyways, so we kind of already talked through a lot of these. The last thing that I didn't finish was talking about fundamental mechanisms. What's key here is that fundamental mechanisms, those nuanced connections, are really what we're missing by only rarely doing domain integration or data fusion, right? We often approach our hypotheses from the perspective of the data inferences and the fundamental models on two separate threads, right? So we're approaching this hypothesis using this experiment, using this observation, and then we're doing a model, that is related to the mechanism that, that has an effect on that observation. And then eventually, once their fidelity is increased enough, we can connect them. That's actually what's happening right now with our spectroscopy and thermal modeling project. We really have no method for automatically tracing back to that fundamental theory other than just, the person who wrote it and reading the paper, especially when you get to those higher order inferences, right? Once you get to the mechanism stacks, getting to that root can be very complicated, especially if you're reading it as as a novice, you know what I mean? Other than those directly stated, right? Fundamental mechanisms and models are going to be inherently incorrect, no matter what, right? Improving them is what we do over decades as we get contradicting data, right? But they're never perfect. And as we approach the compute power to be able to model things that discretely, we apparently have no methods to easily relate this back to those higher order observations other than doing the manual scientific inquiry and testing, right? We find an observation that contests the fundamental mechanisms that we thought were true, so we go back and we look at those in more detail, as opposed to being something that we notice on on the forward pass. So it's my opinion that nascent technology could help us relate those observed signals to the environmental, physical, compositional, and all those other contextual circumstances. We could test different variations of models in comparison to the diverse series of observations or inferences, right? So it'd be very easy to take 8 different fundamental models of fundamental mechanisms and apply them to a large database very quickly to be able to assess how well they model in different scenarios, and then apply that information to the use of that model. We can concurrently integrate the fundamental models and the observational inferences. We don't have to necessarily two-thread them, and they don't necessarily have to be done by 2 different organizations if the data accessibility is solved. And this will also enable that onboard and on-demand reverse engineering of novel data sets. So let's say we do detect something that is anomalous compared to what we've trained on. Well, now we can go back and we can use those fundamental models to try to tell us something a little bit about the data that we do see. Let me make this a little bit bigger for... So I put some of those figures together that I drew out once I had that idea yesterday. Excuse me. Actually, here, I can just do this. OBS stuff, so it's going to look funky, but I think I can boop. And then move you guys over there. All right, how's that look? Cool. Yeah, so I put this together based on those drawings. Spent about an hour and a half, 2 hours yesterday, staring at it, kind of being like, is this what I wanted? I think it does get the idea across. So we have the data, the trends, the statistics, the comparisons, the observations, the experiments, the systems, the samples, the studies, all of the stuff, all of the inputs right at the top. Currently, we connect the distributed knowledge that we have through parallel processing, right? So we take each of these things or groups of these things, and then we make a team and we make a research project where we thread and study those different things. So we get data from server A using company W. We use some new method B in an unrelated sector X, or we do experiments at university C using samples Y. And we do a conference, study D, reviewing new insights from the mission or instrument team Z. The point is that it's dispersed, right? They are going to be connections among them, but they're going to be, the connections are going to occur when it's appropriate for the data type, right? So different domains of data and observation these are the different paths of analysis to reach that data fusion, to do that data fusion and to reach your conclusion, your inference, your knowledge, whatever you want to call it. So there's also hidden and unknown paths. These are just the ones that aren't connected, right? They couldn't be traced or aren't. So those are drawn out there. Now, knowledge integrates, and that's what these arrows are showing, if we find evidence of a manifold property or mechanism. Now, when I say manifold, I'm talking about an underlying property, something that is consistent between them. So you could say two dust samples might have completely different materials, completely different thermal infrared spectral signatures, but the same particle size. Well, that's their manifold, right? So we are finding manifolds among data domains and connecting them. That's one of the fundamentals of science, right? And this is how we create new inferences. We do data and knowledge integration, right? So once a manifold is found, it's connected across domains manually. I go and I look for a paper, I look for that data set, I contact that collaborator, right? I do what's necessary to, find a difference between an observation that causes a trend, or, oh, these two data sets look similar, or, oh, I've seen this in the lab before, and now I'm seeing it in the surface of an environment. Or, okay, I'm going back to heritage work that validates my suspicion. So each of these cross connections entails a significant amount of manual effort, and it doesn't really leave room for continuation and backtracing unless you're going to have redundancy. You're going to have repeated efforts, right? Right. So it requires a lot of backtracing of knowledge, and this is inefficient integration. You can think of it as, okay, once we reach this point, well, now we're going back to confirm it at this stage in the logic, in the line of logic, right? Sometimes it's forward tracing in that you find a data set or a piece of evidence that helps you along in the process, but you can't exactly skip connection, right? So this is what when we talk about backtracing, you can visualize it like this, right? So tracing the fundamental mechanisms and the observations to that integrated knowledge, going from here to here, tracing back to it, it requires a lot of manual context switching. So context switching can be different domains, different sectors, different servers, whatever it is, you're changing the context. And you have to do something in that process in order to do it. You have to relate the data sets in some way, or connect them, or store them on the same place, whatever it is, we're speaking generally here, right? Currently, we connect distributed knowledge through parallel processing, which looks like this. If we try to go back and trace the entirety of the source to the output, well, we're back tracing all the way across all of these different and parallel processed thoughts, and we're effectively wasting a lot of time switching context in a non-logical way, going back and forth and back and forth and back and forth, right? And as a scientist sitting on, one of these paths here, trudging along, and I find something that's over here, there's a lot of additional time and resource and effort that I need to go back and reintegrate that into my thoughts, right? A good scientist will inevitably have a very nice and clean flow, but inevitably that's just, it's never perfect, right? And it's clear that parallel paths are only connecting if the evidence is manifold. It's not in search of manifold, right? If you're in search of manifold down the one thread, you know that you're looking from source to fundamental mechanism to some observation, right? But if you're crossing context, you're not necessarily searching for a manifold. You already have a manifold, and that's how you're crossing context. We should instead be processing knowledge through somewhat like a dendritic pipeline. It naturally maintains the relevant context as it progresses. So it looks a little bit more like something like this, right? It's naturally maintaining the context of the previous domain to the next. So context and new inferences are built around an already integrated knowledge ancestry, right? So we know where this knowledge come from. We know what fundamental mechanisms it could relate to. We know all of that because it's already embedded in that ancestry, in that record, right? So when we trace and integrate knowledge, it's a lot more efficient. Most of it is already built, right? And it's essentially the same as what we do now. It's just right now it's heavily dispersed, right? So this dendritic knowledge integration is really only truly convenient in the era of transformer LLMs and now data saturation, right? The thing we talked about last time. If source data is hosted and correlated on a knowledge integration system, then the evolution of the inference is not going to be limited by that context switching and that manual path crossing, the loss of context and that back tracing, right? It's going to be only limited in what you're doing in that new connection down at the bottom line, right? So it's not a problem of storage. It's not a problem of the network. It's not a problem of the server. Knowledge integration systems are limited by how we interface with them, how we organize and label the data. What kind of inferences and knowledge can we actually include? Right? We can store this stuff. Whether or not it's convenient to access and pull from and reference is a different story, right? It's true that we cannot know what context is going to be relevant, but because it's feasible to trace all of it and then evolve how we integrate that knowledge over time, it's pivotal to avoid unnecessary repeated efforts, right? It's pivotal to forming inferences that are going to include as much of that context as you can without depending on that one researcher having to know all of it or know who to access with it, right? And it allows us to much more easily improve those fundamental models, because every time we add to that knowledge hierarchy or that knowledge ancestry, we're recomparing, we're backtracing easily to that fundamental mechanism. A lot of this is actually quite obvious. It sounds overcomplicated because I'm very good at turning things into generalizations that seem complicated, but it's very clear what's happening here. It's clear that more data and observations means better inferences, right? More knowledge, more knowledge. More data is only helpful if we can organize, parse, and share it. Of course, if we have a bunch of papers strewn around the room, even if they contain the equations for the unification theory, if I can't organize and read them, then I can't use them, right? Sourcing and integrating knowledge is at the root of science. This is, again, very obvious. This is how we do things as scientists and how we do things in all kinds of innovation, right? We source the cause, or the data that we use to make the knowledge, we integrate it with other data, and then we compare it with our old results and so on. Automation of instrument to inference architectures, right? The things we've been talking about, and knowledge integration is already being attempted constantly for discrete applications by tons and tons of experts way smarter than me, right? I am working on something similar for a very particular discrete application. The key here is that as we build up these discrete applications for one domain, they might work with it for a different data set in that same domain. And technically there are a finite number of data domains. There is no incentive currently to share knowledge progress, right? Especially under the IP ecosystem we have today. Intellectual property makes it very difficult to motivate the sharing of knowledge. We have a budding open source community, obviously, for many different things, but that's kind of a knock-on effect of the massive, capital and private equity and consolidation of tech development that we've seen. So people are kind of pushing back by building more open source. So we need to build incentives into the knowledge integration process, right? In addition to the collective benefit that the fully integrated network will eventually offer, we need something that actually encourages the addition to it to build up to that point, right? How could this be actualized? Because it's costly and only profitable once it reaches a certain sphere of influence. The collective good has never been a great, capital building interest, right? It's cool to think about, but it's mostly for marketing, right? Consolidation leads to better coordination, but obviously worse accessibility. If we could do this very quickly if we took the top 5 companies and said, hey, you need to consolidate this into something we can access, but that's not necessarily going to be good for us in long term, right? And you cannot change or work around IP ecosystems and our financial systems. We're not going to start trying to deal with that. That's a separate problem. So we're instead going to create stronger local incentives that help snowball those long-term benefits. So a future-proof solution to the knowledge crisis, a knowledge integration architecture or integrated information, I use the word integrated knowledge network, integrated information system, information integration system, all those different terms. It's whatever you want to call it. It has to be distributed in its control, resources, and infrastructure. It has to be capable of defederation. It has to be domain agnostic and immutable. These are the 4 just most important characteristics of a system like this. Distributed in storage, compute, and network infrastructure, so it's shared across all the involved servers. Peer-to-peer is the only real method that wouldn't involve further consolidation of control that is problematic, right? Decentralized as much as feasible, So we can't ignore kind of the current state of consolidation and how much we would depend on, specific organizations or large funders in order to make something like this happen. It can't be fully decentralized, but as much as feasible to not put our eggs in one basket, essentially. The less spread, the more it degrades over time, and the less it suffers from, or excuse me, the less spread, the more it will degrade and suffer from those knowledge silos that we've talked about, right? And, I don't want to get into the technology side of this too much, but I think it's apparent that the future of information and data storage is in peer-to-peer networks, because we can't become too overly dependent on these large organizations, and these large organizations can't necessarily continue to inflate without becoming too problematic for society as a whole. Defederation refers to the idea that specific servers and organizations will be able to choose to maintain separate knowledge ecosystems, but then involve or absorb other parts of the integrated information network in order to coordinate inferences or provide select context or data. So the knowledge, the data, and the inferences can be defederated from the network. It can be separated. It can be cut off. It can be prevented from affecting the knowledge ancestry and newly integrated inferences or data. So that's when you defederate. So you can have it separated by default, and you can separate it later, right? So let's say there is something that's found to be bad science, right? It was a bad study, or it was, rooted in some kind of ideological toxicity or whatever it might be. We remove it from the network. However, the key is that it's still immutable, which I'll talk about after we talk about domain agnostic. So it just means any mode of data. You can have any type of data, any observation, any inference, any knowledge, anything can be integrated. We need to be able to accommodate all data types. So how can we defederate but be immutable? Well, while the active state of the system can be changed, an archive of the traceability of the system remains incapable of alteration, right? So traceability is maintained by a shared distributed ledger, and this provides multi-party verification and access, and a historical record with integrity that is also easily scalable, right? So we can always, any independent verifier can go back and look at the root of this stuff. The key is getting the right information in, and also allowing all people to conveniently and easy add their context, so that if there is conflicting context, we can actually investigate that and provide the evidence without making a particular a claim or verifying one way or the other, right? The key is to provide the information, not necessarily the conclusion. So what will this look like? What kind of methods will be used? Well, I didn't finish it. So, this is kind of where I left off, because this meeting tomorrow is going to be my first introduction with this individual. And, I think they're familiar with me because of my work on one of these specific models and some connections on some government projects I've been working on. And so I'm going to have to like play it by ear, but I'm preparing all of these thoughts in case they're very receptive to, the discussion, where it's a lot of these types of meetings. I'm going in and playing it by ear with a lot of different notes that I could work from, just because I want to be able to scale the possibility, the scope, the outcome, the project, the funding, the whatever we could get to continue this project at a high level. Because obviously I'm really invested in this and really passionate about it, but I'm poor, broke, and busy. So it's not really going to be feasible for me to accelerate this to the scope that I hope, and it's going to be important that I meet people and sell it to the best of my ability. So talking through this with you guys has helped. I appreciate you listening.